Okay, this is the second video for section 1-3 in your pre-calculus books. This video is going to cover end behavior for function graphs. End behavior is another application of limits. Essentially what we're talking about when we say end behavior is we're asking ourselves, how does the function behave at either end of the graph? Okay, so in other words, we're looking at the end behavior, what happens to the values of the function itself as x increases or decreases to infinity. Okay, what we're talking about there is as we move to the right or towards negative infinity, and the left, which is towards infinity. Okay, now we don't want to get caught up too much in the notation here because most of the notation is always exactly the same. So every single time that you do one of these problems, the left end behavior is going to be the limit of f of x as x approaches negative infinity. In other words, as we move our x value to the left towards negative infinity, what is the function doing as we move to negative infinity? Okay? That notation is always exactly the same. Now, if we look at this particular function, f of x, as x goes to negative infinity, the function is going up to positive infinity. Now that won't always be the case, but in this case the left end behavior is going to infinity. As the x values decrease to infinity, the function increases to infinity. That's what we're seeing on the left end of that graph. Now we're looking for it in proper notation, which would be the limit as x approaches negative infinity of f of x equals infinity, which says as x gets really, really small, f of x gets really, really big. On the right end, the only difference in the notation is that instead of saying as x approaches negative infinity, we say as x approaches infinity of f of x. So look at the graph again. As we move to the right, the function is going to negative infinity. So we would say that equals negative infinity. In words, we're saying as the x values increase, the function decreases to negative infinity. Okay, so don't get caught up in the notation. The notation is exactly the same 99% of the time. See, what we're looking at is the only part of this notation that ever changes are these values. Everything else in the notation is always exactly the same. This notation in the left box is always the left end. This notation is always the right end. Then we just have to look at the graph. So here are two more examples. We're going to write out the end behavior for each. So for A, the limit as x approaches negative infinity of r of x would be the left end behavior, and the limit as x approaches infinity of r of x would be the right end behavior. In both cases, on the left end and on the right end, as x goes out, the function goes down to negative infinity. So both ends would have negative infinity for their answer. On h of x, the limit as x approaches negative infinity of h of x. On the left end, as we move towards negative infinity, the function is going down to negative infinity. On the right end, the limit as x approaches positive infinity of h of x. As x increases, so does the function. The function also increases to positive infinity. And that should be how quick this goes. Now notice, once again, the only values that changed were what the function is doing at those ends, the left end and the right end. Okay, here's two more, same deal. We're going to do these as well. So for g of x, the limit as x approaches negative infinity on the left end, the function goes to negative infinity. On the right end, the limit as x approaches positive infinity, the function also goes to negative infinity. Now f of x, they're not trying to trick you here. I know the graph is hand-drawn, but notice that instead of going to positive infinity or negative infinity, the graph is approaching this line. Well, that's the line f of x equals 0. So we would say the limit as x approaches negative infinity of f of x, the function is going to 0. It is approaching that line f of x equals 0, y equals 0. The same thing is happening on the right end. As we approach positive infinity, the function is also approaching 0. Okay, so there's your end behavior. Okay, so take a minute, pause the video, try E and F, and then we'll go over those answers as well. So pause the video now and give them a shot. All right, so for k of x, we have that same situation again. If you look, on the left and the right ends, the function is leveling out. Okay, so for k of x, the limit as x approaches negative infinity of k of x, the function is approaching this line, which according to our scale is the line f of x equals 1. Same thing on the right side. The limit as x approaches positive infinity of k of x, that function is also approaching our dotted line, which has a value of 1. So both the left and right end behavior of k of x should be 1. For p of x, the limit as x approaches negative infinity of p of x, on the left end we are leveling off to this line, which is the line y equals negative 2. And on the right end, we are approaching a completely different line. On the right end, we are approaching 0. So the left end behavior approaches negative 2, the right end behavior approaches 0. Okay, now these require a graphing calculator, so I am going to hand sketch the graphs as I pull them off of the graphing calculator. But you are going to need to break out your graphing calculator that you checked out from me. If you do not have a graphing calculator, you can go to Desmos, DESMOS.com, where there is a free online graphing calculator. So, for the first graph, f of x equals x squared minus 3x plus 1. The graph is a parabola. We are looking at a parabola that passes through 2 points in the positive x area. Looks something like this. And again, we don't really care about specific values. All we care about are the end behaviors. So the limit as x approaches negative infinity of f of x, it goes to positive infinity here. It's going to positive infinity as x goes to negative. Same thing for x approaches positive infinity of f of x. That end is also going to positive infinity. So there's your end behavior for the first one. For letter B, this one's a little bit trickier to put into the calculator, so please be careful. What you need to do in your calculator is type in parentheses 2x minus 3 and then divided by x plus 1 also in parentheses. If you don't put parentheses around the top and the bottom, you're not going to get the correct answer. Also, make sure you're hitting the subtraction button here, not the negative. Okay? When you type that in and you hit your graph button, you're going to discover that this particular graph has an asymptote at negative 1. Okay, so if we're looking at the graph, there's an asymptote at negative 1. The graph comes in and approaches the value y equals 2. It has a horizontal asymptote at y equals 2, which is the result of these lead terms having coefficients of 2 and 1. 2 over 1 is 2. So the graph is going up and out, and then it's coming back in low and going back out again. So our limit of g of x as x approaches negative infinity is 2, and our limit as x approaches positive infinity of g of x is also 2. It is approaching 2 on both ends. Finally, for the graph of negative 10 over x squared that is also a graph that has an asymptote. That asymptote is at x equals 0. So it's this line right here is the asymptote. It's going to be a little bit harder to see, so I'm going to use a highlighter to draw it. Okay. The axis itself is the vertical asymptote. The horizontal asymptote is going to be the other axis, the y-axis. And the graph itself is going to come in along the x-axis and go out, and then it's going to come back in along the axis. So it should look like that on your graphing calculator. Once again, we don't really care about the specific values. All we care about is the limits of this function as we approach negative infinity. So the limit as x approaches negative infinity of h of x, and the limit as x approaches positive infinity of h of x. And on both ends, our end behavior is approaching 0. That does it for end behavior. Thank you for your time.